Hello! Hello, everybody! Welcome to the LIUniverse. I'm Dr. Charles Liu. Please call me Chuck if you feel like it. And I'm here with two great people that I'm very proud to have with us today. First, our co host, Allen Liu. Hey, Allen, how's it going?
Hi, it's going good.
All right, terrific. And our special guest, Paco Holguin. Paco, how you doing? Good to see
Good.
you.
Hi.
You are an expert in computational astrophysics, including things like stuff that blows up out in space. So I can't wait to ask you about those things and talk to you about some of that cool fundamental science as well as other neat things, because I understand you are also a science fiction aficionado, an expert, a person actually that has like a reading list waiting to be read. Is that true?
I'm trying to be. I'm trying to be an expert. Yeah.
Spoken so modestly. I appreciate that. Thank you so much. Okay, we start today, as we often do, by discussing today's joyfully cool cosmic thing. Now, this might seem a little mundane to you all, but I think it's super cool because, as it turns out, neutrons, you know, those things, protons, neutrons, electrons, right? They decay. They actually do not stick around unless they are bound to protons in nuclei or ions and stuff like that. And so it has been a very important question. How long, on average, do neutrons sit around if they're unbound to anything else before they decay? Right, Paco? I mean, this is like stuff that we tried to learn in like elementary cosmology, right?
Yeah. No, definitely. And that's actually I'm glad you brought that up. It's one of the things that when I first started getting into physics as a kid, the decay of the neutron was just something that I fixated on for some reason.
No
Uh,
kidding.
yeah, I remember asking my middle school science teacher about it, and he was like, I don't know. like,
Apparently, recently, at Los Alamos National Laboratories in New Mexico, a very interesting experiment was conducted whereby it has been measured now after looking carefully at almost 40 million neutrons floating around in special environments that we now think that the half-life of the neutron is 877 plus or minus zero point 0.5 seconds. So that's like between 14 and 15 minutes. It's 14 and a half minutes.
yeah.
If you realize that in life, if everything were not made of protons and neutrons together, but just made of neutrons, the entire universe would be 15 minutes old. And that's it. We'd be done. Well, 15, half of all matter would decay, and then half all neutrons decay, another 15, another 15, another 15. So a few hours, we'd all be kind of subatomic particles. But we are not. And Los Alamos National Laboratories is indeed a cool place to do this because it is, I would say, I don't know, what would you call it, Paco? The most storied, most historically interesting nuclear science lab in the world.
Yeah. I mean, just historically, that's where a lot of things happen. A lot of people gathered.
Yeah, Los Alamos National Labs is in the northern part of New Mexico. It's a little bit away from Santa Fe, a little way away from Albuquerque. And what is the science that you do, Paco? And how does Los Alamos National Labs or the people there influence what you do?
So in general, I like simulating things. I want to put something on the
Ah,
computer and I want to see it run. And that probably stems from a lot of the video games that I played in high school and growing up.
Nice.
It's just, I want to play video games with real life.
excellent.
And so I also really think that magnetic fields are really cool. So I
Oh,
started learning about them and I was like, I want to do something with magnetic fields, and that was what I did in
neat.
undergrad. I did a lot of I did a lot of research at MIT's Plasma Science and Fusion Center, and I just continued to learn that
Oh,
magnetic fields are cool. But I'd always wanted to
yeah.
do, space has a lot of interesting things, and when I went to graduate school, I was kind of looking for what to do. There's a lot of things to study, and so I was like, well, here's my advisor, who would become my advisor. He works on galaxies, cool, but he works on magnetic field stuff, and things related to that. And I was like, all right, I think that's going to be my advisor. I'll talk to him, and it worked out.
Nice.
I make galaxies, I set them up, and then I let
Mm.
them run. And these galaxies, they have stars, and they eject energy and supernova, and the simulation evolves. But the particular part here is that they have cosmic rays.
Oh.
So cosmic rays would be just free floating protons and other subatomic particles that just plow through space. Yeah. And so they're just like particle accelerator in the universe that causes them. Based on some measurements done in observations with the composition of cosmic rays, we kind of know that cosmic rays, while they're moving close to the speed of light, they do also kind of they have a resonance time in the galaxy. And it's more than, it's on the order of millions of years. And so we're like, okay, they're moving at the speed of light, but based on other constraints, we know that they're staying around in the galaxy. And so what causes, just from, first university physics courses, what causes charged particles to change direction? That's magnetic fields.
Magnetic fields. Of
yeah.
course.
And so,
yeah.
And so there's a lot of uncertain theory as to how this is done, how cosmic rays interact with the magnetic environment of the galaxy. But models like that is what we try to put into these galaxies. And so there's like a fluid of cosmic rays that kind of exists separately than the gas, but it kind of exchanges energy with it.
Neat.
And that's really the basis of my thesis work, is trying to interact with that.
That's fantastic. Trying to talk about cosmic rays as like a perfectly normal physical phenomenon, when we know that in comic books what they did was created the Fantastic Four and Doctor Doom and things like that. But that's actually something I'm waiting for them to get into the Marvel Cinematic Universe, because they haven't gotten there yet. But the Fantastic Four, of course, was for me as a kid what maybe video games were for you, because I loved comics and I saw those things in cosmic rays. Do cosmic rays actually have the potential to mutate human beings and turn them into superheroes?
I think there was some estimate that they cause some percentage of computer errors on
really?
Yeah, because they'll just punch through the earth.
So cosmic rays are they're going through us right now.
Yeah.
Ooh, so maybe I could become Mr. Fantastic.
Yeah, so they'll do something, right? But it's more of a random process. So
that's too bad. That's okay. Oh, it's comforting to know that like we don't get destroyed by them instantly or anything like that. But the cosmic rays are there, and I think that's really neat for you to say. Now, you're saying that they actually live for millions of years in the galaxy, but they would be gone within 100,000 years or so, because that's about how wide the Milky Way galaxy is, right? So they'd go flying through, but they get captured in this big circle,
or even less
if they're going like that.
If they're going on the thin part of the disk, they'll spend less time.
So right. So what happens then as they're doing this? If they're circling and they're creating what's essentially like a gigantic particle accelerator, right? Kind of like the Large Hadron Collider or something, which is about 20 miles long. But you're talking about something that's more like trillions and trillions of miles long. How are you going to simulate that? How do you stick that into a computer and figure out how that works?
Yeah, and the answer is you don't. It's the same analogy as to why when we model, like, let's say, in an engine of a car, where we model like thermal effects, right? Like there's some energy and then gas expands, and then we have this thing that allows us to extract energy and do useful work. When we do that, we're not really modeling the individual atoms or the motion of particles, and it's kind of in the same way, because we know that there must be some sort of confinement of them. If you calculate what that sort of length scale is, as long as you simulate things that are larger than that, like larger than the confinement length scale, then you can kind of treat it like a relativistic fluid. Like it's like a fluid, but it has a relativistic equation of state.
Wow.
Yeah.
So fluids flowing at close to the speed of light, and thus they wind up acting very, very strangely compared to
Well,
like water on Earth.
it's kind of it's not moving at the speed of light. It's kind of moving along with the gas because you know that the bulk motion kind of moves with the gas.
I see.
Yeah. Now, if you wanted to simulate the cosmic rays themselves, there's smaller scale simulations. You just can't do that as a galaxy. Galaxies are way too big.
That's fair.
Yeah.
Too bad. All right. Well, now is a good time to get a question. Do we, Alan, have questions from a student or from one of our patrons?
Yeah, so we're going to start off with some student questions. We got a couple of them. The one that we're going to start off with is this one from Will from Pingree Astronomy Club. Will is asking, what are other extreme objects in the universe besides black holes and neutron stars?
Now we already know cosmic rays are kind of extreme, but they're not extreme like objects or extreme particles to some extent. Paco, what do you have for that?
So I do want to mention cosmic rays again because not all cosmic rays are the same. Not all cosmic rays. They're kind of they exist on a spectrum. Some of them, the ones that I was talking about, they're the slower kind. And now there's these things called ultra high energy cosmic rays, which are moving extremely quickly. They sort of have more energy than the LHC would be able to give, and they're the most energetic ones that have been found. I find myself thinking a lot about them, and it also leads into a lot of sci-fi too. I think the most energetic particle that has been found has been nicknamed the "Oh my God" particle. I don't know if you've heard of this before, but
no,
it's moving.
Oh my gosh!
Yeah, it's moving so fast, so close to the speed of light. It can't be the speed of light because it has mass, but it's moving so close to the speed of light that I remember someone saying, and I think I confirmed this too, just by myself, is if you race them across the galaxy, a photon in that cosmic ray. By the end of the galaxy, the photon's only ahead by like a meter.
Whoa,
that's crazy.
So it's
3 feet after 100,000 years. Unbelievable.
Yeah, I would categorize that as an extreme object. And
definitely.
The sci-fi thing that I think a lot about is just that, like, and I've done this. I go on like Wolfram Alpha and calculate the time dilation factor on this, and it's just incredible. Like, just insane amount of time dilation moving that close to the speed of light.
For those members of our audience who aren't familiar with time dilation, right, that's an effect of the special theory of relativity that Albert Einstein explained. The faster you move compared with the speed of light, then actually the time that you experience is actually reduced, right?
Yeah.
So, for example, if I'm moving faster than you are, I actually will wind up aging less than you for a brief period of time, right? But what you're talking about here is extreme to the point where this cosmic ray literally has aged almost nothing in the thousands and thousands of years that it's traveled. Is that right?
Yeah, and I find myself just imagining, like, how would it feel like to be this single particle? Like, it doesn't have a mind, right? But yeah, it's and this is the oh my God, like the OMG particle.
As opposed to the so-called God particle,
yes,
which is the Higgs boson, which actually isn't the God particle. They didn't want to call it the God particle; it just became part of the title of a book, which wound up selling really well. But this oh my God particle is it was a detection. Is that right? Something happened once a long time ago?
Yeah, so it was a detection in October 1991 with a camera called the Fly's Eye camera that was looking for cosmic rays out in Utah.
Oh.
And it had enough energy that it's all the energy of like a baseball moving at like 60 miles an hour packed into a single particle.
Whoa.
So, a baseball's, I don't know how many particles, 10 to the 23 is. But instead of that, all those particles, it's just one, probably a proton. We're not sure if it was a proton. That's crazy.
That's amazing. So if that particle actually had hit any one of us, and had actually been able to impart all of its kinetic energy into us, we would have been knocked over as if we'd been hit by a fastball.
Yeah.
Well, a changeup, I guess.
Yeah, it's not quite a fastball, but still.
That's amazing. One little particle. Wow.
Yeah.
Okay, I can understand why they decided to call it the OMG particle. That's terrific. So how do you compute that? how do you do that computational work there, Paco? Because many members of our audience love video games too, and love simulating stuff, and love thinking about this thing that you're doing right now. So, what is the guts of it in non-specialist way of talking about how do you actually go about computing or simulating these kinds of amazing objects?
Yeah, that's something that I feel like it's a continuous process to learn. When I first
Mm-hmm.
started doing a lot of simulations, I wasn't really working with a lot of the sort of guts of the simulation, and I kind of understood it like in a rudimentary sense, like, oh yeah, like I did some math in college and kind of just solve the equations and then things come out of it. Like it sounds reasonable. But I think when you start learning more about this, you realize that these equations are very complicated, and they're you can't just sit on a piece of paper and solve them and try to do it for the whole
Yeah.
galaxy. Especially when you have like a star goes off here, and then something else is happening here, and it's all moving. I only recently I decided to take a graduate math class during my PhD,
Ooh.
just
Uh-huh.
just because I was like, I kind of want to see how this is done, and we kind of built up the theory. And what it is just people have thought of really clever ways of solving these equations on like large with a lot of like data points.
Ah.
And so honestly, like at
Yeah.
some point, it just turns into an art. Like when you start reading a lot of like the choices that people have made or why they've made these things, it's because you're solving the equations. It's too hard to do it exactly, so we're going to make this approximation, but this approximation is terrible under certain circumstances. So someone has spent like several years of their life focusing on this one problem, so they toss in
Yeah.
a band-aid and they just keep band-aiding it. So it's almost like a Rube Goldberg machine. Honestly, like
Wow.
at some point, like you're like, yeah, this textbook says I have to make this choice, and so I'll do it. Yeah, like,
Yeah.
Gee.
and I've had simulations in my PhD that galaxies going, and suddenly, faster than the speed of light, the galaxy just blows up. The entire thing,
Oh no.
like,
It just explodes.
yeah,
That's spectacular.
there's no like trying to figure out why it happened or what. It's an instability. Like there's too many things going on. It's not exact, and so you
Wow.
just have to talk to someone who knows what they're doing and be like, all right, what band-aid should I put on this so that it doesn't explode?
Yeah, because we don't see those galaxies exploding all the time.
Yeah, and so you're like, all right, well, I try this band-aid. Did the galaxy still explode? Yes. All right, try this other band-aid.
What a great lesson, actually, for all of us. I myself, having never observed a galaxy exploding, uh, we often don't realize how much of this computational stuff or the scientific stuff is still quite unknown, and you're still experimenting. That's a great
Yeah.
lesson for us all. Thank you, Paco. That's really neat to understand it, and we should realize that everything is not all settled. There's still lots of things to tweak. I imagine that you've probably, in your work, tweaked this thing that people said don't tweak because it'll blow up the galaxy, and you tweaked it and it blew up the galaxy. And then
Yeah.
you're like, well, maybe I could find something else to tweak so that it won't blow up, and then it becomes, like you said, another band-aid or an art or something. And that's research. That's science, right?
That is science. Yeah.
Oh, that's wonderful. Alan, we have another question.
We do have another question. So this is another question about extreme stuff. Is there an upper limit to the size of a black hole? And that's a question from Jayla from North Andover.
Now, Paco, you've made galaxies blow up faster than the speed of light. Can you put an upper bound to a black hole?
Yeah, I like this question because it's a question that I've Googled repeatedly throughout my life. I really
Oh,
like black holes. And so I've
Yeah.
Googled a bunch of, what's the hottest temperature? What's the longest wavelength? Like questions. As far as I know, I think there is probably not an upper limit, although I guess the astronomy answer is that some people have proposed that if you make them too big, then they kind of have inefficient accretion. So like they can't get stuff fast enough after they get so big. And so there's kind of like there
oh.
might be an effective upper limit just because they just can't eat efficiently anymore.
So theoretically, you can add mass as much as you want, but on a practical level, sooner or later, nothing falls in because at the surface of the black hole, the celestial radius, it's just not attractive.
Or it's more that like stuff has to fall to the black hole for it to get there, and I think eventually like it. I don't remember too much, but maybe it just clears out its area, and then just stuff doesn't fall in that fast.
Do you know if it's like 10 billion, 100 billion, a trillion times the mass of the sun, or
I mean, I know the heaviest black hole is something ridiculous uh, like several billion, probably like 10 to the 9, right, or more, solar masses, which
yeah,
is
billions of times?
which is like ridiculous because you start talking about like clusters of stars and like parts of galaxies that weigh that much, and so here you have an
Yeah.
entire black hole. So black holes can get still very very massive apparently, like and have been observed at those masses.
So it sounds like there is no upper limit, but we haven't found the limit yet. Or if there is a limit, we haven't found it yet. So far, we're up to billions of times the mass of the sun. Okay, great question. Thank you so much. And yes, we must not underestimate the power of a search engine in our efforts to learn about the universe. Paco, is there anything else you really want to share with us? Is there anything really cool in terms of like science fiction stuff that's happening now, or any kind of neat thing that's happening where you are, what you're doing, those sorts of things?
Yeah, well, I guess I think it'd be useful to mention. I didn't specifically mention anything I've done at Los Alamos. Um,
Yeah, we were
so
talking about Los Alamos. Source. Tell us about it.
yeah, I think that kind of stemmed from I was looking, as I kind of mentioned, with the computational stuff. Sometimes it kind of you can get into these all of details and it's challenging. And I was looking for just to get a fresh perspective on something else. So I really wanted to do something that has nothing to do with my thesis or anything, and so.
Mm-hmm.
So I just, applied to go work at Los Alamos through a summer program, and because of the pandemic, it ended up being remote. And so then because
Mhm.
things were still remote because of the pandemic, continued on. I just continued working there, and then I went the next summer with another group, and so I've contributed to some machine learning projects, and
Ooh.
so one of which was actually trying to apply machine learning to mathematical algorithms.
Okay.
Oh.
And so yeah, I actually ended up getting experience with machine learning, which I think was just a very useful thing to do. But one of the things that I appreciate about being in a sort of pseudo academic environment, like it's not like strictly a
Yeah.
university, but it's not strictly like a private research lab, is that the people that I work with are incredibly diverse in terms of their academic backgrounds, um,
Oh.
which I think is fantastic. Like I haven't worked with an astronomer yet, and I've worked with like
Ha.
a bunch of people. I've worked with people who have PhDs in nuclear engineering, statistics, geophysical, fluid dynamics,
Wow.
and it's really cool to be like tackling the same problems and being interested in the same things, but having different
Yeah.
perspectives. Because like one of the projects that I was working on is related to the ChemCam, which is on the Curiosity rover
Oh.
on Mars. So using that data that they acquire, they shoot lasers at rocks and they observe the light
Ah.
that comes from the rock.
Yeah.
And so with that, you can kind of estimate what the composition is of the rock without like going to it and picking it up and analyzing it. And so I was
Wow.
working with some machine learning to do that. But the cool thing is that like the people I was working with, most of them were like statisticians or computer scientists. Um,
Oh.
and so it was just interesting from that perspective, being more having more of a background of like the physics and the planetary science and the part of it, whereas they're coming from it from this is data and there's some representation of that data and there's various statistical processes that you can use to extract that data. Um,
Yeah.
Wow.
so I've really enjoyed that, and I'm kind of sad that now that I'm finishing up my PhD, that'll come to an end, because I'm not going to
Oh.
go work at Los Alamos, but it was definitely a
Uh-huh.
solid
Wow.
solid 2 years that I enjoyed.
That's spectacular. I'm really glad you shared that with us. Thank you so much. And Alan, of course, being formally trained as a mathematician, I'm sure would find very interesting the kinds of artificial intelligence work you're doing to solve mathematical algorithms. I think that's cool.
Yeah, it's definitely a really exciting area of research.
So tell me, what are you doing after this? I know you're almost done with the University of Michigan. And then what are you going to head off doing? Tell us all about it and tell us how we can follow you.
Yeah, what I really wanted to continue is I wanted to continue doing research and computational research. Where I ended up, or where I applied and got accepted to, is what I think is precisely what I set out to find in my job search. I meandered through the job application process, and I somehow ended up where I wanted to be. And
Wonderful.
That's at the Applied Physics Lab at Johns Hopkins University.
Oh, in Maryland.
In Maryland, yeah. And so it's a permanent position.
Wow.
And so I'm going to be, the group focuses on general space topics. That could be national security things. That could be space probe related things. And so I just such a broad group, and they just work on space things and a lot of simulations and a lot of interdisciplinary work. And when I was talking to them during the interview, I feel like I clicked with almost everything that they were talking about. And so I'm just excited to get there and just start kind of grabbing onto different things to do.
Oh, I think that's wonderful. Yeah. The Applied Physics Lab is where several famous planetary missions have been based, right? I think maybe New Horizons or Near Shoemaker, a few of these others. That's just a wonderful place. And if it's anything like the environment you described at Los Alamos, where you could really spread your wings and do creative things, I think that's spectacular. That's wonderful. Good for you. Hooray. Well, I will ask you right now if you will come back again sometime in the future, and we'll chat more about science fiction, science fact, and science, all kinds of stuff. And we'll geek out and have more fun. Would you do that?
Yeah, definitely. I thought this was really, really cool, and really excited to sort of talk and cover a lot of things that are interrelated. So I'd definitely be really happy to come back and talk more about stuff.
Consider that a high probability likelihood then. Thank you so much, Paco. Allen, thank you so much, as always, for your superb activity. Much appreciated. Thank you again, Paco. We'll talk again soon. Congratulations on the things that you're doing now and the things that you will be doing soon at the Applied Physics Lab. And thank you, everybody out there. Thank you, audience, for being with us today. If you want to support this show, please go to our Patreon page and give us an opportunity to produce even more wonderful shows and conversations. Until then, thank you so much. Thank you for being a part of the LIUniverse.